In this section, we are going to be taking a deeper dive into something that we mentioned in the previous section but didn't go into detail on, and that is the ozone layer. The ozone layer is a part of the atmosphere made up of ozone, a chemical composed of three oxygen atoms bonded together. Unlike the gaseous oxygen that we breathe, which is just two oxygen atoms bonded together, O2, ozone is O3. You can see a simple comparison between their two structures here. And the defining characteristic of ozone as a chemical is how unstable it is. The third oxygen atom will break off from the molecule very easily. And that third oxygen atom is extremely reactive. It will react with most things it comes in contact with. And because of this, exposure to oxygen is harmful to humans and living organisms in general because it will react with biological molecules, including DNA, and cause damage to them, which can lead to cancer. For this reason, when you find ozone down in the troposphere, which remember is the lowest level of the atmosphere that reaches about 7 miles up from Earth's surface, it's considered a pollutant. But when ozone is found in the stratosphere, which is where most ozone is located, it actually plays an essential role in maintaining livable conditions on Earth. We'll talk more about that in just a second. But first, where does ozone come from? Ozone is actually generated in the stratosphere, a natural process called the ozone oxygen cycle. This cycle begins when UV radiation from the sun hits a regular old molecule of oxygen gas, which remember is just O2, two oxygen atoms instead of three. And that energy causes it to break apart into two lone oxygen atoms. Then each one of those oxygen atoms grabs on to an intact molecule of oxygen gas available, and together they become O3, ozone. Then this ozone will absorb more UV radiation from the sun, breaking it back down into lone oxygen atoms and oxygen gas. And we will end up back where we started. So you can see how this is a cycle. Um, And as long as the rate at which ozone is being created is the same as the rate at which ozone is being broken, then this cycle sustains itself and remains in balance. However, that balance has been disrupted by human activity in recent decades. And that's a problem because the fact that this ozone oxygen cycle absorbs UV radiation as it runs its course means that it actually serves as a buffer that protects the Earth below from exposure to excessive levels of UV radiation. So, a little more about UV or ultraviolet radiation. There are actually three different types of UV radiation that the sun produces. UVA carries the least energy and therefore is the least harmful. You can see it represented in the lighter orange color on the left of this image. UVA is not absorbed in the ozone oxygen cycle, so it makes its way through the ozone layer and travels to the Earth. So, this is the type of UV that you are trying to protect yourself against when you wear sunscreen. When we say it is the least harmful, that doesn't mean it's harmless. That just means that it's not as harmful as the other two. UVB carries more energy than UVA, but 90 to 95% of it gets absorbed by the ozone layer, so we're largely protected from it. UVB is the one represented in the darker orange color in the middle, and ozone is actually the only known gas that absorbs UVB, so that gives you a sense of its importance. And finally, UVC. It's the most energetic and most harmful. This is the one shown in red on the right. But thankfully, the ozone layer absorbs virtually 100% of the UVC and buffers the surface of the Earth from exposure to it. So, the bottom line is that the sun is throwing out all sorts of harmful radiation, and the ozone layer blocks the worst of it, which makes it possible for life on Earth to carry on. You can imagine that the depletion of the ozone layer would represent a major threat to the planet. And ozone depletion is exactly what happened in recent decades over some parts of the planet. We know this because scientists have been measuring levels of ozone in the atmosphere since the 1920s and monitoring changes. In 1985, the British Antarctic Survey first reported their data showing the thickness of the ozone layer over Antarctica being depleted. In other words, the ozone layer was getting thinner, and furthermore, the region in which this thinning was happening was getting larger. In this image, you can see a representation of the size of the ozone hole in the same month every year between 1979 and 2019. And as you can see, how for how long of a time the hole was getting worse. And then staying about the same, and in this past few years, you can see how it's getting smaller. The healing trajectory that the hole is now on is thanks to environmental protection laws that were passed to stop the human activities that were causing the hole in the first place. So, what are those activities? Well, humans were releasing chemicals into the atmosphere that were throwing off the balance of the ozone oxygen cycle and therefore causing what we know as ozone depletion. Ozone depletion occurs when the rate at which ozone is being broken down at a greater rate than that at which it's being created. So, in other words, the ozone is disappearing faster than it is being made. Here in yellow, you can see the step that generates ozone from oxygen gas, as we discussed previously. And this step absorbs UVC radiation. Then in pink, you can see the breakdown of ozone back into oxygen gas. And this step absorbs both UVB and UVC radiation. Remember how we said that ozone is the only known chemical that absorbs UVB? So if you don't have enough ozone around to absorb that UVB because it's not being generated fast enough, then more of that higher energy UVB starts to break through down to the Earth's surface. This is a problem. So why is it happening? Well, people invented chlorofluorocarbons, also known as CFCs, and started releasing them into the environment. CFCs are man made chemicals that are made of chlorine, fluorine, and carbon, hence the name. Here is a little cartoon of one. They are extremely stable and non reactive, while also being capable of absorbing a lot of heat energy, which made them great candidates for use in aerosol sprays like shaving cream and hairspray, and also were commonly used as coolants in refrigerators and air conditioners. Because they are so stable, they are also extremely persistent. And when they are released down here on the Earth's surface, they remain intact and swirl around in the troposphere until they eventually make their way up to the stratosphere. And once they are in the stratosphere, they get exposed to UV radiation. And although they are extremely stable, the UV radiation is enough to break them apart. Chlorine atoms will break away from the rest of the molecule. When those chlorine atoms encounter a molecule of ozone, they will react with it and pull off one of the oxygen atoms. This effectively destroys the ozone and transforms it into oxygen gas, removing the opportunity for the process to occur in a way that absorbs UVB radiation. But what's even worse is that the chlorine atom won't hold on to that oxygen atom. It will drop it off a, on a different free lone oxygen atom, which effectively creates another molecule of oxygen gas and also frees up the chlorine atom so that it can keep doing this process over and over again. So the effect that a single chlorine atom is multiplied astronomically. One chlorine atom repeats this process and destroys about 100,000 molecules of ozone, resulting in this phenomenon known as ozone depletion. And again, without all of that ozone, more UVB radiation breaks through and reaches the surface of the Earth. The last question we need to address is why the heck this process was specifically localized over Antarctica. Well, Antarctica has some unique conditions that make it more susceptible to a high concentration of ozone depletion. In the winter, air obviously becomes much colder and therefore denser over Antarctica. And this creates an area of high pressure that gets isolated from the air in lower latitudes that experience milder temperatures. Within this high air pressure area, a polar vortex forms, which circulates the air up into the stratosphere. Normally, we said that the stratosphere contains no water vapor, but the polar vortex drives ice crystals way up into the atmosphere where ozone, chlorine, and other chemicals attach to their surface. And the surface of the ice crystals creates the opportunity for those chemicals to come together and react with each other. Furthermore, as ozone becomes depleted, the polar vortex keeps air isolated above the Antarctic region and prevents it from blending with the air at lower latitudes. This keeps the phenomenon concentrated and amplifies it in this specific area. So ozone depletion occurs at an accelerated rate over Antarctica. And therefore, Antarctica serves as a sort of canary in the coal mine, a pre warning sign of what was coming to other regions of the globe if chlorofluorocarbons continued to be used and released into the atmosphere. Fortunately, Antarctica is not an inhabited region, but the amount of UVB that was getting through the hole in the ozone layer would have caused a substantial increase in the incidence of cancer if that hole were located over populated regions, and also would have seriously damaged plants and important marine producers like plankton and algae. So, recognizing the threat and knowing what was at stake, the international community banded together and passed a treaty called the Montreal Protocol in 1987. The Montreal Protocol was a plan to phase out production of CFCs, and it had nations agreed to cut CFC production in half by the year 1998. There have been several follow up agreements since the original 1987 treaty that focused on advancing more cuts and including other ozone depleting chemicals such as halons, methylchloroform, carbon tetrachloride, and hydrochlorofluorocarbons. The treaty has been a success, and at this point, most countries have phased out production of ozone depleting chemicals. And as a result, the ozone layer is slowly being restored. All over the world, ozone levels are rising and restoring the thickness of the ozone layer. And in the area where the depletion was the worst, that hole over Antarctica, is projected to recover to conditions on par with the year 1980 by the year 2066. For the US's part, compliance with the Montreal Protocol has taken the form of an amendment to the Clean Air Act, which requires the EPA to create programs that end the production of ozone depleting substances, ensure that refrigerants and halon fire extinguishing agents are recycled properly, identify safe and effective alternatives to ozone depleting substances, ban the release of ozone depleting refrigerants during the service, maintenance, and disposal of air conditioners and other refrigeration equipment, require that manufacturers label products either containing or made with the most harmful ozone depleting substances.